So it's a real pleasure to hold this seminar. It's a community that I usually don't talk to, so it's of course an interesting challenge for me as well. And so the idea, yes, is to tell you something about my research. So the reason why it's difficult is because I know that I'm talking mainly to experimentalists, I think, and I'm a theoretical physicist. And on top of that, of course, your research direction is completely, well, it's different than what I do. I usually work mainly for collider physics. So what I would like to do is, tell you something about opportunities and challenges in precision physics at the LHC. And so in order to start, I think the most natural place to start is the Standard Model, and in particular the Standard Model after the Higgs discovery, given also the fact that I think as of today, we are in a sort of special moment for particle physics, at least for collider particle physics. The Higgs has been discovered in 2012, and this has brought many people to say, I think partly correctly, partly not, that in a sense the Standard Model is complete, right? So we have discovered everything that we could discover. There was at least till today no supersymmetry, no extra dimensions. We haven't discovered any signs directly of dark matter, for example. And so some people have started losing hope, in a sense, and saying that there is nothing more to do in collider physics. And hopefully I will convince you, if you need convincing, probably you don't, that this is definitely not the case. So this is definitely one of the goals of this talk. And the reason, there are many reasons why this is not the case, but the main reason why this is not the case, at least to me, is because the Standard Model is not only made of particles, but it's also made of interactions. So there are, of course, all the particles that we have discovered, including the Higgs boson, but there are also the interactions among them. And if we look in particular at the ways the Higgs boson interacts with the other particles, which is given by the last terms in this Lagrange, and this is what you usually get if you buy a t-shirt at CERN, then the truth is that we don't know much about many of these terms. So if we start looking a little bit at these terms more closely, we see, for example, that the first one, well, the last one actually, in the Lagrangian, as I wrote it here, as I copied here, is the so-called Higgs potential. And it's true, we have seen the Higgs, so we have seen the particle, if you want, the oscillations of the Higgs field, but we don't know much about the form, the shape of this potential here, which is also, in some sense, what determines how the spontaneous symmetry breaking mechanism really happens for real. So we have seen the Higgs, but the potential is just a toy model, in a sense, the simplest realization that we could imagine. And we can ask a lot of questions, right? We can ask, are there more minima, for example, in the potential? So could there be a transition between different minima? Are there even more Higgses? Or is there maybe a sort of microscopic model that explains, like for superconductors, how the spontaneous symmetry breaking mechanism happens? Now, the problem is that in order to answer these questions, what we would need to do, at least for how we understand things today, is measuring the Higgs self-couplings. And this is extremely complicated at the level that even considering the whole LHC lifetime till 2035, more or less, we can only hope with current techniques that we will get to measure these self-couplings with more or less 4 sigma. So actually see them more or less with 4 sigma, not even really 5 sigma. So of course here the situation is not that nice. Then let's see actually what happens for another term of this Lagrangian. Well, the other term that we also don't know much about, well, we know a bit more about this term, but still we don't know everything about it, is the term with the covariant derivative, so-called, which tells us, in a sense, how the Higgs boson couples to other vector bosons. This term is actually mathematically very well understood because the shape of this coupling comes from gauge invariance. So we like and we understand a lot the mathematics that is behind, the mathematics and the physics that is behind this particular coupling, contrary to the shape of the Higgs potential. And we also have seen much more about it, right? Because this term is what tells us, for example, that the Higgs can decay to vector bosons, and is how the Higgs has been discovered, for example, in 2012, looking at the Higgs decaying to Z bosons. The problem is that, of course, there could be anomalous couplings. There could be couplings that are not predicted by this model. And in order to see whether these couplings are there, we will have to do very precise measurements of these couplings and compare them to theory. I will get to this more in detail in a second. But the most important and the most interesting part of this Lagrangian, most interesting because it's the one that we have the most direct access to, and is the one in which we have the most opportunities to make discover, if you want, in the very near future, is this term here, which is what we refer to usually as the Yukawa interactions. I say here that this is the most mysterious, and the reason why I call it the most mysterious is because, in a sense, it's the ugliest part of the Lagrangian, if you allow me to put it like that. It tells us why particles like quarks and leptons have masses, but there are a lot of parameters that are not determined in this Lagrangian that we have to measure, and this is already not very nice. And also the shape of this coupling is, in a sense, very arbitrary. Now, the point is that while we don't understand theoretically why this term in the Lagrangian has the shape that it has, on the other hand, it's incredibly important because it's at the base of all chemistry as we know it, and if you want, also life, right? The simplest way to see this is if we think about, for example, at how the Higgs boson couples to quarks, right? So we know that there are 3 families of quarks organized like in up and down types quarks. So we have up, down, charm, strange, and top, bottom. And there is something very funny happening in the parameters of the Lagrangian. So we know that the way the Higgs couples to these quarks determines their masses. And now if we look at the masses of these particles, we see that somehow something funny happens, and namely, only for the first family of quarks, the hierarchy of masses is inverted. So the up quark is lighter than the down quark. For the other ones, it's always the other way around, right? The charm is heavier than the strange, and the top is heavier than the bottom. This is very important because if we go exactly and we look at matter that makes everything that we have around us in every day, matter is made of protons and neutrons and, of course, electrons. And the only difference between protons and neutrons is the quark content. So as far as we understand it today, we have 2 up quarks and a down quark in the proton, and 2 down quarks and 1 up quark in the neutron. And the small difference in mass, the fact that the proton is a little bit lighter than the neutron, comes in a sense exactly from the fact that the up quarks are a little bit lighter than the down quarks. And so this is responsible of the fact that the proton is stable, and in the sense that there can be chemistry and there can be life. And it's very strange that this thing comes from a pattern that is very strange and not understood, right? These masses seem completely random. Of course, it could be that they are random, but the opportunity that we have to understand, the only chance that we have to understand if there is a pattern, if there is something, is trying to extract as much information as possible from the LHC and from future colliders and from any other idea that we can come up with about this part of the Lagrangian. So also, why is this particularly important now? Well, this is important now because, as I said, well, as I haven't said yet, but I want to say now, well, the LHC is the machine that we have working now, and is the very first machine that is able to probe these couplings directly. If you want, it's the very first machine that is able to probe the electroweak symmetry breaking mechanism directly. And the proof of what I'm saying comes from these very nice measurements that were done 2 years ago now by CMS and Atlas for the first time, which are measurements about the production of a Higgs in association with a TT-power pair at the LHC. This is particularly interesting because you see, is for the first time we see really the Higgs coupling to top quarks directly, and so we know that at least that the idea that we have that the Higgs has to couple directly to quarks, at least to the 3rd family of quarks, because the top belongs to the 3rd family of quarks, cannot be that wrong. Now, the interesting thing is that this measurement has been done with a very small amount of data compared to the total amount of data that the LHC will collect. If you look at this nice plot where you see the luminosity as a function of the year, you see that we are here now. So we have collected 140 inverse femtobarns at the end of run 2. Now we are in this long shutdown. Run 3 will start again soon, probably a bit delayed due to the coronavirus as well, I guess. But you see that the amount of luminosity, the amount of data that we will collect till the end of the LHC lifetime is huge. So we have collected only 5% of what we expect to collect till the end of the LHC lifetime. And so these measurements that we have just made can actually be turned by, well, in a couple of years already, into precision measurements that can tell us a lot, much more precisely about the way the Higgs couples to at least the third families of quarks. And if you look directly at the numbers, for example, if you take this paper of 2018, for example, from CMS, you see that already from these measurements in 2018, with a small amount of data, they could already do a very nice measurement with statistical experimental uncertainties in the end, which are of the order of well, between 15 and 20%. And the interesting thing of this is not just a statistical uncertainty, but it's comparing this to the theoretical uncertainty on the background and on the signal that is of the same order. Now, the problem is that improving for us as theorists here is very complicated, and this is what I will tell you about in a moment. While for the experimentalists, for the experiments, this will happen in a sense naturally, because in the next years, there will be, as I said, so much more data collected that definitely one can expect without any doubt that the statistical uncertainty will go down even up to a factor of 6 for high luminosity LHC for the full data set. And so definitely you see that we have the opportunity to test that the standard model is correct, or at least if you want, the way the Higgs couples to top quarks is correct with a precision of a couple of percent. And another reason why I think precision physics is in general important, this is just a completely different example where people have measured and studied theoretically the production of pairs of vector bosons, in this particular case a Z and a W boson. And you see also here, for example, comparing experimental data, these blue dots, with calculations in a so-called next leading order, which is the first order in perturbation theory, which for this process is already a rather complicated calculation, and then the next order of the perturbative calculation, which is next to next leading order, which is an incredibly complicated calculation. And you see that without this calculation here, the difference is huge at the level that one could almost already claim new physics. Right? So it's very important that as theorists, of course, and also as experimentalists, we are aware of the fact that, of course, there can be mistakes on the theory side that make us discover new physics or think that we are discovering new physics, but there are also simply problems sometimes in not taking into account enough orders in the perturbative expansion, okay? So this is another explicit example. Now the question is, okay, I tried to convince you in a sense that it would be interesting and it would be nice in order to extract as much information as possible from the LHC, in particular for the Higgs sector and its couplings to quarks, to do theoretical calculations that are as precise as the experimental data, and we are talking about a couple of percent of precision. And so the question that I want to ask here is actually, can we go that far? So can we do calculations that are so precise? And it's not completely obvious that we can do that, because the LHC is a hadronic machine. It collides protons, hadrons, which are strongly interacting. So the environment where these collisions happen is a very dirty environment in a sense, due to the fact that there is a lot of QCD going on. So we have these protons, the protons collide, there are a lot of gluons going around, and then the particles are produced and they decay and a lot of things happen. And so we have to be able to have this whole picture under a very good theoretical control. So can we do this? Well, the reason why we can do this, and we can actually estimate how far we can go with this, is a very important word for collider physics, for theoretical physicists to do collider physics, but also for experimentalists, I think. That is the concept of factorization. So factorization is something that happens in everyday physics, right? We're used to that, where it's practically the idea that high energy physics and low energy physics are decoupled in a sense, or if I do an experiment on the moon and something else happens here, the two things are in a sense completely unrelated. From the point of view of QCD, this is particularly important because we know that in QCD, when we consider processes at very high energy, then the strong coupling goes down, it becomes small, and so thanks to asymptotic freedom, the theory becomes perturbative. So we can do calculations that are reliable, but only for very high energy. And the question is, how are we sure that all these low energy gluons that fly around in our collision don't invalidate completely the calculation that we have done? The reason why we are sure about this is exactly because of factorization. We can compute rather reliably, in some cases very precisely, in some other cases less precisely, how large these corrections are, and we can estimate these corrections to be in general of the order of lambda QCD divided Q, where Q is the hard scale of the process that we are considering. So lambda QCD is the non-perturbative QCD scale, which is a couple of hundreds of MeV, and Q is the hard scale. So for a typical LHC process, this can be 10 GeV or 50 GeV or 100 GeV and so on. So it's clear that without any issues, we can, at least for relatively simple finite states, we can keep this thing under control at a few percent level. This is not an issue in general. The second problem is, of course, we still need a way to get a handle of the non-perturbative physics. Even if it factorizes from the perturbative one, we still have to know how to account for it. And this is what is, in a simplifying way, is included in so-called parton distribution functions, which are the probability to extract partons from the colliding hadrons. And also these PDFs, these parton distribution functions, of course, they cannot be computed. There have been some ideas now to compute them on the lattice, for example, but in general, they cannot be computed because they are non-perturbative. But we can fit them from simple experiments. And these parton distribution functions have been fitted in different ways, taking a lot of data from different experiments. And now we have them under very good control, again, more or less at the few percent level, at least as long as the energy scales that are relevant for the LHC are concerned. So everything that is non-perturbative, in a sense, is under control. There are, of course, other complicated aspects that I'm a little bit neglecting now. So when we really do these experiments and we want to see what happens in the collider for real, so we need parton showers, we need hadronization, because, of course, partons hadronize, we need detector simulation. So all these things need to be under very good control, and they are more and more. A lot of people are working on this. But so the thing that I want to focus on is trying to get the last piece of the puzzle under control at the percent level of precision, which is what we call the hard scattering. The hard scattering is exactly what happens in this blob in here, indicated with H. And it's the only part of the whole picture that we can compute reliably, and if you want, in a mathematically sound way, more or less, using quantum field theory. I'm going to switch now from this generic picture to the hard scattering, and I'm going to tell you a little bit more about this, which is the part that I'm mainly interested in, and trying to tell you what are the challenges for us that we are trying to address now in order to be able to do the calculations that I told you that we want to do at the precision that we need. So hard scattering means just, in some sense, the simplified formula that I wrote up here. So we want to compute a cross-section for elementary particles, for example, a quark and an anti-quark that collide and produce two gluons. And the way we do this is that we compute, first of all, this object M, which is what we call a scattering amplitude. We square it, and then we integrate it over the phase space of the external particles. Of course, this integration of a phase space can be arbitrarily complicated if you're interested in very differential observables, if you want to look at rapidities, if you want to look at angles, if you want to look at transverse momenta, and so on and so forth. So of course, this integral becomes very complicated in practice. And what we want to do is being able to do this integral numerically, because for general differential distributions, this becomes impossible. It cannot be done analytically. So let's first of all look at this scattering amplitude, because now this is the object that we can really compute in perturbative quantum field theory. So in QCD, for example, assuming that alpha strong is small, we can expand this thing in alpha strong and then compute so-called leading order, next to leading order, next to leading order contributions. So if we start leading order, the way we compute it for real is that we usually use Feynman diagrams, right? So we write the Feynman diagrams needed for this calculation. And the Feynman diagrams that contribute at leading order are so-called the three-level Feynman diagrams. There is an example here for two quarks that collide and produce two gluons. And these calculations are very easy. They are very well under control. We have beautiful techniques to do this calculation with as many particles as we want, even without using Feynman diagrams. The problem is that these calculations are very, well, the precision of these calculations is very bad. They are not that accurate. And so if we do typically one of these calculations, and we get only a very rough estimate of what the cross-section is. Usually the precision is around 100%. So we need to go at least one order higher. And if we go one order higher, at so-called next leading order, things already start becoming a little bit more interesting. And the reason why they're more interesting is because we have two different types of contributions that have to be taken care of together here. One type of contribution is what we call, in jargon, virtual diagrams, and the other ones are what we call real diagrams. What is happening here is that, of course, I'm going higher in perturbation theory, so I have loop diagrams, like this virtual gluon here, and that's why they are called virtual. But I also have to add diagrams where there is one more gluon in the final state. The reason why I have to do this is because these two classes of diagrams, when I compute the cross-section, they give contributions at the same order in alpha strong. And in particular, this, when one of the gluons here becomes unresolved, so it becomes soft or collinear to another particle, and so we don't see it in the detector, then this thing produces an infrared divergence, a pole, that somehow would make this integral blow up. But this pole cancels exactly with the same pole that is produced by computing this loop integral here. So somehow there are two difficulties. We have to be able to do this integral, and then we have to be able to put it together with this one where the phase spaces here are different. So that there are two different integrals that I have to do, one on the phase space of 2 particles and one on the phase space of 3 particles. And I have to do all of these numerically. So I'm treating like objects that are divergent. I have to do it numerically. So I need to find a way to put these divergences under control, which are called subtraction schemes, which can be very complicated. But if I manage to do that, and this has been done at next to leading order, then I can put these things together and I can get a result. Now, the nice thing is that if I manage to do that, then the precision of these calculations is already much better than leading order. We go between 30 to 10% as a rule of thumb. It's still far, though, from the couple of percents that I was talking about before. That is what we would need in order to exploit LHC data at best. Now you see, as I said, there are two problems. So one of the problems that I want to talk about, I want to say immediately that there is this issue of the infrared divergences, as I said, has been solved. But the nice thing here is that also these one loop virtual amplitudes, this part here, are also completely understood. And I want to tell you how this understanding happened, very, very schematically, of course, without going too much into any mathematical details, just to tell you what made the difference, okay? So the difference happened, say, 15 years ago, as you can see from these papers, when people realized, well, they put together some pieces of knowledge that they had already since several decades, actually, or at least 1 or 2 decades. And they realized that every possible one loop amplitude where you can produce as many particles as you want, so you could like produce, I don't know, 3 Z bosons, 2 Ws, a lot of Higgs bosons, a lot of gluons, whatever. Even if there are a lot of particles, actually at the end of the day, each one of these amplitudes can always be written as the composition into elementary building blocks, which are always the same. So these building blocks are a basis, in a sense, for every amplitude, and they are completely general. So they're fine for every amplitude. The only thing that changes is the coefficients, right? When we go from one amplitude to the other, some of the coefficients will be 0, some of them will be different than for another amplitude, and so on. So these coefficients keep inside the information about the particles that we're really dealing with. And what happened in these years is that people developed techniques to compute these coefficients very efficiently. And also, but this was known already before, they managed to compute all these building blocks analytically in terms of very simple functions that we all know and understand. So in terms of rational functions, in terms of logarithms, which I think we all know, and the only maybe a little bit more difficult function that popped up in these calculations, but there was everything, is this so-called dilogarithm, which is this function here. And this was studied and understood by mathematicians almost 300 years ago. So there is really no issue with that, right? Every computer code has implementations of these functions. Everyone knows them and understands them, so there is no issue. So in a sense, for every amplitude, we always have all these ingredients under control. Now, the problem is that, as I told you, this is not enough in general to get the right precision. So we have to go one order higher. Now, when we go at least one order higher, then this whole pattern that I told you about before becomes much more complicated. Something similar happens. So I have so-called double virtual diagrams where I have 2 loops. I have real virtual diagrams where I have 1 loop and one more external particle, and I have double real diagrams. Now, these 2 pieces here are not a problem, because I told you I can do every 3-level calculation. I can do every 1-loop calculation, no problem, thanks to the developments that I explained before. The issue is computing this guy here and putting them together, because of course also the infrared divergences will be much more involved. Now, there have been a lot of developments here. I don't have time to talk about this. This would be completely another talk. What I want to talk about is actually the 2-loop part here. Also because, this I didn't say. This takes us to the more or less the right precision that we're aiming to, so say 5%. But yeah, I want to focus on the 2-loop amplitudes. Because thanks to all the developments that happened on the infrared subtraction part, so putting together these pieces and getting something finite, actually for most of the calculations that we're interested in, these objects here are today the bottleneck, is what prevents us from being able to give a prediction for a process, for example, TT bar Higgs, with the right precision that we need. Okay. So in spite of the fact that these things are very complicated, there have been a lot of developments, and the way to see how many developments there have been, I think, can be summarized by this very nice plot that was originally done by Gavin Salam and then was updated by Leandro Ceri last year, where we see how many of these higher order calculations have been done in function of the year, right? So you see that the first calculation started in 1990, but there have been like very few calculations, and it took like years to go from one calculation to the other. But then starting in 2014, there has been a real explosion of calculations. And then after that, there's been a slowdown again. So these explosions actually pushed some people to think that we had made it, right? We cracked it. We can do everything in the next reading order. Actually, this is not the case, as this part of the plot shows. So the reason is not that there is nothing left interesting to compute, but it's because things have become too complicated. And so I want to somehow tell you a couple of words, at least, of course, without going too much into detail, of what happened here, why there was this explosion, why the explosion has slowed down again. So what is it that we cannot do? What is it that is complicated? So what is complicated is exactly modeling processes that have more than 2 particles in the final state, so-called 2 to 3 processes in jargon. For example, this is a Feynman diagram for the production of 3 jets at the LHC, or processes that have inside heavy particles, for example, top quarks. And these are problematic already at the 2 to 2 level, where we have 2 particles that enter and 2 particles that go out. You see now that if you mix together these two kinds of complexities, then you get exactly Feynman diagrams that are needed to compute the process that I told you is, in a sense, the holy grail of LHC physics now, which is the production of pairs of tops with a Higgs boson. So this process that we desperately want to compute at a couple of % level of precision is actually one of the most complicated things that we can imagine today. Of course, I mean, we can imagine more and more complicated things, but this is very complicated and it's also very important. There are also other similar processes where instead of having an Higgs boson, here we have a Z boson or a W boson, and these things are also have been measured very precisely. They are as complicated from the theoretical point of view, and so if not more in a sense, and also can give you a lot of information that can be background for this kind of process here, and can be background also for some dark matter searches and for many other things. So how do we go about it? Just to tell you where the complexity comes from. Well, so the idea to do these calculations is to do something similar to what I told you happens at one loop, right? So at one loop, I told you before that every amplitude can be decomposed into universal building blocks. And so if we manage to find an algorithm to compute these coefficients and to compute the building blocks, then we are done. Now, at two loops, the thing is much more complicated. And the reason is because on one hand, computing this, so the decomposition still applies, right? But first of all, the number of building blocks is huge. We don't know what is actually the final number yet. Second, well, computing these coefficients is very complicated, really from an algebraic point of view. You need like huge computers from a computational point of view. You need huge computers, and then your RAM memory is going to die. And so there are a lot of like, unfortunately, non-conceptual, but practical problems that one has to solve. And there has been a lot of interesting development here in trying to find more clever ways to do this that is not just brute force, putting it on a bigger computer. And then there is there are the integrals, right? So the corresponding building blocks, that is things that are called master integrals, that unfortunately are not anymore as easy as the one loop ones. We don't know how many there are. We cannot compute all of them. And definitely we know that the functions that come out when we do these calculations are very complicated, and we are relatively sure that there are functions inside these integrals that no one has ever encountered and ever classified. So mathematicians don't know these functions, right? So this is a real conceptual complexity in a sense. And we all know that computing integrals is probably the most complicated thing that one can do. And so it's very difficult to solve this problem in practice. So let me say a couple of words about this, if I manage, yeah. So how do we compute these integrals and why are they complicated? Well, the reason why they're complicated is because actually these integrals contain inside informations on the so-called branch cuts of the scattering amplitude that we are computing. What do I mean with that? I will show it explicitly in a second, but I mean that there is a branch cut in the amplitude whenever some particles inside the diagram can go on shell, so can be produced for real. The energy is high enough that these virtual particles in the loops can be produced. Of course, the higher is the number of loops, the more possible configurations I can get inside the loops that can go on shell. And so the more complicated this branch cut structure will become. Now, the fact that this branch cut structure has to be there, it's really physics, right? It's not invented in a sense. It has to be there. It's not spurious. And it comes from unitarity and causality. So really, quantum field theory tells us that when particles go on shell, this is the simplest example that we can imagine. This is the photon that through an electron loop produces another photon. When the energy of this photon is high enough that these particles, these electrons can go on shell, so the threshold energy is 4m², there has to be a branch cut, a discontinuity in this amplitude. And in fact, we see that when we compute them analytically, whatever that means, this is a one loop amplitude, these things are expressed in terms of so-called multi-valued functions. Mathematically, these are functions that have branch cuts. So there are square roots, for example, and then there are logarithms, as I said, and then there is dilogarithms and so on. So now I think no one of you would object to the statement that if I write this diagram as in this way, then this thing is an analytic result, and we are happy, we are done, right? We have completed the calculation. But still, I want to spend 2 words to say, what do I mean when I say like analytic result? So in which sense can I call this result analytic? Why am I happy? Well, the reason because I'm happy is, to put it in a simplistic way, is because it's written in terms of known functions. But I mean, of course, I could take an integral and give it a name and say that it's a known function, right? This is doesn't really help me. What helps me is that I understand these functions. I understand, for example, functional relations. This is an example of a functional relation between logarithms, right? I understand their branch cuts because I want to be able to understand these branch cuts. These are physics, right? The imaginary parts that come out from the scattering amplitudes. I mean, this is quantum mechanics, physics. So imaginary parts give rise to interference, which is what makes quantum mechanics quantum mechanics. And I want to be able to do series expansions because I want to be able to solve, to evaluate these things numerically. And the only way that I have to evaluate functions numerically is doing series expansions. So I need to have these functions under control. That's why I call this result analytic, because I can do all of these things. So what I would need to do when I go to any kind of calculation is somehow understand what the space of function is produced by these Feynman integrals, And in order to do that, I would need to classify these functions and to understand how to do analytic continuation, to expand them in series, to evaluate them numerically, and so on and so forth. And now, what I just want to give you a glimpse of is what has been happening in the last couple of years, is that we are understanding that actually there is a very nice geometrical interpretation of where these functions pop up. And that this geometrical interpretation is connected to the theory of complex Riemann surfaces, which probably you don't know what they are, but that's, and if you do, it's fine, and if you don't, it's also fine. I will not say anything profound about this. But the nice thing is that this geometrical interpretation allows us to classify these functions much more easily, and so it makes the calculation of Feynman integrals more simple or simpler. And I want just to give you an idea of why this thing that sounds very scary, maybe for some people, Riemann surface, so how does this help me, and what is this thing? Well, a Riemann surface is nothing complicated. So the simplest Riemann surface that you can imagine is the so-called Riemann sphere, which is something that mathematicians call a surface of genus 0, which means that it's a surface that doesn't have any holes. The sphere is a two-dimensional, if you want, sphere, but is actually a one-dimensional complex surface, in the sense that this is just a complex plane, right? It's nothing more complicated than taking the complex plane and closing it onto itself in this point here. So if you want, here there is the point 0 in the complex plane, and here there's the point infinity. So you've taken really the complex plane and you've closed it as a sphere. Now, it turns out that mathematicians can tell you that the only functions that can be well-defined on this complex plane, in a sense, are rational functions. There is nothing else. So functions like this one, that have poles, A, which live here on the complex plane. And if you imagine to do an integral of a rational function of this kind, what you're going to get is a logarithm, right? So this is, again, the simplest multi-valued function that you can get is if you take one of these rational functions and you integrate them, and then you get a logarithm. The nice thing is that once you have understood this, which the way I said it, I mean, I haven't said anything complicated, but one can formalize this mathematically in a very precise way, then you also know that the only thing that can happen on this sphere, if you keep on doing more and more integrals, because imagine that we are doing multi-loop integrals, so we have to integrate many times, we keep on integrating these functions over and over again, and we are going to get objects that are not that much different from the logarithm, and there is what people call today multiple polylogarithms. If you look at this definition, I mean, you don't really have to look too much at it, but you see that you're just integrating over and over again something that looks like a logarithm, 1 over t minus something, right? I don't want to say anything about these functions, right? I wanted to say their name because this pops up everywhere. And indeed, it's just thanks to the fact that we understood this, that we understood that these functions happen and work in this way, and we can study their relations, we can study their series expansions and so on, that all these calculations here, these explosion of calculations between 2014 and 2017, say, became possible. It was really thanks to the fact that we understood how to handle these functions, to do series expansions, numerical evaluation, and how to develop methods to integrate Feynman amplitudes, Feynman diagrams in terms of these functions. So it was a mathematical breakthrough that brought to a physical breakthrough, as you can see here. Now the problem is that we have hit a wall, right? And the wall is exactly because starting at 2 loops, unfortunately, these functions are not enough. And there is actually more going on. And this more that is going on, unfortunately, happens exactly in, for example, T bar Higgs, and these very interesting processes with masses that are the ones that give us the most information about this, the electroweak symmetry breaking mechanism. This slide can look very technical, but the important thing of this slide is that if you study this diagram, what I just want to say in here is that inside of this diagram, you find some new objects, which are the sunrise integral that have like gotten a lot of interest in the community in the past couple of years. And the reason why this object is there is because the reason why this thing is interesting is because this thing generates, instead of a rational function, when you want to compute it, it generates a square root of a complicated polynomial, which geometrically corresponds to an elliptic curve. And the nice thing is that once we have understood, now these details are not important. What is nice is that once you see this, then and if you have understood that there are these Riemann surfaces and there are functions with branch cuts that live on Riemann surfaces, you think about it a little bit, you talk to mathematicians and so on, and then you realize that the only thing that you have to do is generalize your picture from a Riemann surface that is a sphere, so a Riemann surface without a hole, to a Riemann surface that has one hole, which is a Riemann surface that is called the genus 1 surface. So the geometry changes, of course, things become more complicated, but it turns out that this thing is entirely equivalent to this elliptic curve, this elliptic object that appears in here. And once you move from here to here, you can then repeat the same construction that you have done for these functions and build other functions that will be uglier or better, more complicated, easier, and so on. That depends on the point of view. But then you can classify these functions with the very same methods that you use to classify these ones, and you can do a lot of progress. And this is what has been happening like in an explosive way in the past 5 years, understanding these functions and try to make calculations like the TT bar Higgs one doable. Unfortunately, we're still far from making them doable because those calculations are even more complicated than this. So these functions here are not enough. And still, it is the first step. And now that we have understood how to do these things in general, we can hopefully more easily generalize what we're doing. And these things, they appear everywhere, right? These are just some examples of processes where these new objects appear. Also, of course, beyond 2 loops, one can go also to 3 loops. For example, this is the production of a Higgs boson in 2 gluons. But this brings me already to my conclusion. I didn't want to go too much into detail. If you have more questions, of course, I'd be happy to answer them. But what I tried to do with this talk is, well, convincing you, first of all, of something that you knew already, and namely that the LHC is turning into a precision machine. It was a discovery machine, but it turned into a precision machine and is providing us very precious details on the electroweak symmetry breaking mechanism. And that in order to profit from this as theorists, well, the experimentalists have a lot of work to do, but as theorists, we also have a lot of work to do. And the nice thing is that this work, which is, of course, on one side is very technical and very complicated and requires very, very complicated calculations, can be approached by brute force, and many people have tried, but also is actually, what people have found is that the only way to crack these very complicated calculations is doing like a breakthrough, if you want, in our understanding of the fundamental properties of the mathematics of quantum field theory. And this is actually, every time that we have made a small step in that direction, a breakthrough in this understanding, then new calculations have become possible and have become much easier than what they were before. So there is definitely a lot of potential, both from the mathematical point of view and from the formal point of view, and then from the physics point of view. And so hopefully with these developments and everything that has been happening, so phenomenology for so-called complicated, complex final states in next leading order is becoming, well, is coming within reach. And so I'd say stay tuned, and thank you for the attention.
Thank you very much, Lorenzo.
Was I on time? Because
yes, I was putting the -5, but
yeah, no, because you know what? When I turned off my video, then I stopped seeing you as well, which is probably not the best thing that could happen.
That's okay.
Yeah.
So, are there any questions for Lorenzo? Is it next to next? Is next to the third leading order?
NQ below. Yeah, we know we have some NQ below calculations already, yes. But for very simple final states. So for example, if you want to produce only one Higgs, or for so-called Drellian, which is the dilepton production.
Yes,
these calculations are relatively much simpler than many of the ones that I was showing here. Sorry, let me try to. They're much simpler. They're more like similar to something like that, right? To a so-called 3-point function. You have the 2 quarks that enter, and only one thing comes out, either a Higgs or a W boson or a Z boson that decays to leptons. And these things are known up to NQ below. Actually, that is also interesting because there you see that when you compute Higgs cross sections, you actually see that next to leading order calculations are actually still the precision is still very low. It's still like between 10–15%. So you really have to go to NQ below in order to go down to 5%. So yeah.
Okay, that was a curiosity. Thanks. Are there any other comments or questions?
I hope I didn't kill anyone, or that I didn't say two stupid things, but
Jeter?
Yes, thank you for the talk. Can you hear me?
Yeah, I can.
Okay, good. I was just curious about timescales in terms of the calculations versus the experiment. Which is going to drive which, or are you about on the same timescale?
It's very difficult. So for some things, theoretical calculations are somehow so much easier. So yeah, it's tricky. So for example, this process that I think is one of the most interesting, what I was saying, like production of TT bars and, for example, a Higgs boson or a Z boson or a W boson, if you actually take Z boson and W boson, the experiments have already today 5% precision, while our calculations are around 15%. And the calculations are very complicated. So I don't know when it will happen that we will manage to get the same precision. It could be in 1 year, it could be in 5 years. I have no idea, because for us it's also very non-linear, right? So we don't have, for us it's not just enough to accumulate more data. We have to find a way to do the calculation, which sometimes could never happen in principle. I mean, we know that it will happen at some point, because some people will at some point do it completely brute force. Maybe you can do it numerically, and if you really want to extract a number out of it, right? There are other cases where the experiment is actually already so precise that we know that we will never manage to catch up. For example, for Drellian, for Z production, they already have precisions at around of the per mil. And for the discussion that I did at the beginning, we will never get to that precision. We cannot get below 1% because there are non-perturbative effects. There is stuff that we don't have any control over at the moment. So it has, I would say that maybe if I look historically, now in the last years of the LHC, actually the LHC has been driving the theorists more than the theorists have been driving the LHC. In the past, it has happened that theorists were doing calculations before, but now with the LHC running, they are really giving us a hard time, I would say.
Thank you.
All good time.
I have a question. In dark matter community, they always ask this question that when we have to stop to search for dark matter, given that we haven't seen anything so far. So similar question I got is that if, for example, you do all these calculations and you don't see any difference between the Monte Carlo, what is the next step?
Yeah,
for this?
I think is a very good question. It's what I was trying to say with the, so we can think of it like this, right? So for example, I think we all agree that QED, right, quantum electrodynamics is like understood and is accepted, right? We know that in a sense it's a correct theory, but at least up to some energy scales. But so would have we been able to say this if we, for example, had tested QED only at the 10% in some particular energy scales? I mean, the reason why we are so confident that QED is correct is because we have measurements and calculations that agree with, I don't know, 10 digits, 12 digits or something like that. I mean, it's astonishing, right? So now, I mean, what I was trying to show at the beginning is that we have barely seen, well, we have seen the Higgs, not barely. We have barely seen it coupling to third family, the third generation of leptons and quarks, because we have seen the Higgs decay to bottoms, we have seen the Higgs decay to taus, and we have seen the Higgs coupling to tops now. We have still completely no idea about whether the Higgs is really coupling to the other quarks as we think that it does, right? What I was trying to write here. And we have no idea why things are how they are. So I think that as long as there is the possibility to learn something from the measurement, right? So this model here predicts something special, right? And I can do this calculation and I can compare it with the experiment and hopefully finding a deviation, then I think I'm well justified to do that, because it's really the only thing that is somehow a question that we know is answerable, at least at the given precision. We know that we have the machine running, and we know that we can do the calculation at that precision. Of course, if you ask me, for example, does it make sense to do Drellian or something else at n5 then of course there it starts becoming complicated, because not just because the experiment can get to that precision, but there are two other things that cannot work out, as I said before, like non-perturbative physics and so on. So there is definitely a place where a physicist you want to stop, and that place is when the experiment cannot anymore compared with the theory at that level. But we are so far from that now. Then there is a second, if I can take 1 minute to say that there is something else on top of this, at least for me and also for many people. The point is that these calculations, they are also teaching us a lot about quantum field theory. This is what I also try to say. And since they teach us about quantum field theory, I think it's not completely unjustified to say that if you're really interested in understanding the details of quantum field theory, you want to do these calculations to find general patterns. Once you've found the general pattern, that general pattern can maybe tell you even how to go beyond that thing, right? You don't really know what is going to happen. So there is also a formal interest that I think is not completely wasted, in a sense, in doing these things. You don't really know, right, what's coming out of it. But if you discover that there is a beautiful mathematics, for example, that describes perturbative quantum field theory at every order, right? From a practical point of view, it could be useless, because we know that we will never be able, first of all, QCD after some loops doesn't make sense anymore, right? Like every theories after some loops don't make sense anymore, but who knows what we can learn from that, right? So it's, in some sense, it's free research, right? So that you can find like justifications also of this kind, I think, which are fine to me. I don't know if this answers the questions, but
that did answer the question.
Yeah.
Thank you very much.
Any other question or comment? Sean, go ahead. Thanks.
Just immediately, just want to say, like, really, I am impressed by moving from a genus 0 to moving from genus 0 to a genus 1 Riemann surface that's been improving your calculations. Does that not also mean that your simulations have to, like anyone doing simulations on that higher order Riemann surface, they now have a completely different lattice and now completely have to change as well?
Well, I think so. So when you're talking about simulations, are you thinking about Monte Carlos, or what are you thinking about exactly?
No, not Monte Carlo. More, is anyone working on sort of direct simulation using the new lattice?
Okay, really. So non-perturbative physics. No, from that point of view, I think it doesn't impact that thing in any because you see, these people, they never really see perturbative quantum field theory. See, there is another issue there, right? These structures that we see, they are perturbative. What they do, right, is that they take the Lagrangian and they somehow put it on a lattice completely numerically, and then they try to compute something correlation functions out of that. But the physics that they see and the structures that they see, in my understanding, I'm not an expert of lattice, but they are completely unrelated in a sense, right? You never know if these methods can help them as well, of course. But in general, I would say that they are unrelated.
Thank you very much. That clears it up.
Any other question or comment? If not, I would like to thank you, Lorenzo, again.
Thank you for the invitation, and thank you for coming. Yeah.
Thank you for joining.
For joining, yeah, coming is probably not the right word, but for joining.
If you could please send me the slide.
Of course.
So while you already start talking, I start recording. So would it be okay if I upload the recording?
Unless
Unless
I've said something that I should be ashamed of, I think you can.
I don't think
that
so.
I didn't realize.
I will release, and in case I will cut.
No, it's fine. It's fine. I can stop sharing right now.
Yes.
Yeah.
Okay.
No, it's fine. So of course you can upload.